Hello, my name is Ben Davis, and today I'll be introducing you to chemical equilibrium. Now, one word about equilibrium. Equilibrium shows up in more than just chemistry. Definitely the fundamentals we'll talk about today show up in biology and biochem. And the general concept, the concept that some system gets to a low energy state, it also shows up in physics and in the social sciences in economics. So to demonstrate this, I'm going to talk first about a very important industrial reaction called the Haber-Bosch process. This is where you take three equivalents of hydrogen gas and you react it with one equivalent of nitrogen, and these form ammonia, also gas. Now this is a very important reaction to the world, human society, because we run this reaction at about 150 million tons a year. The nitrogen can be, the ammonia can be used as a fertilizer directly, but also as a precursor to fertilizers, and hence how we improve our food production. So to show how equilibrium applies to this reaction, what I'd like to do is plot how these reagents change with time. So what I'll do, because we're dealing with gases, on the y-axis I'll do the partial pressure of the reactants and products. That will be represented by P sub x, where x is the reactant or product, and then I'll have time on the x-axis. So we'll start out with only reactants. The first case. This will be hydrogen. We'll start off with quite a bit of hydrogen. It will decrease as it reacts, and then eventually it will flatten out. We don't need as much nitrogen based on the stoichiometry, so we'll start at a lower value, and this won't be as consumed, but it too will flatten out. And lastly, we'll produce some ammonia. So we'll start at 0 by definition, and we'll produce some ammonia, not much. This reaction doesn't produce much product. Now, by definition, when a reaction has gotten to the point where its partial pressures or concentrations cease to change, so I'm going to say that's about here, based on the flatness of the lines I made, that area represents, by definition, equilibrium. Now, the beautiful thing about equilibrium reactions is it doesn't matter how you get there. So you can start off with just reactants, just product, or a mixture, and it will still come to equilibrium. Now, that would look like this if we, rather than starting off with reactants, if we start off with products, we'll start off with just a little bit of ammonia this time. And so in this case, we have a positive amount of ammonia, and it will decrease slightly as it decomposes in this case. 2 ammonias will form 3 moles of hydrogen and 1 of nitrogen. So we'll start off with 0 nitrogen, and this will grow to a constant value. And the hydrogen will also be formed. And since it forms 3 equivalents, this will go to a higher level. So in this case, we just started with only ammonia, only the product to start. But because this is an equilibrium reaction, the ammonia breaks down in order to find its equilibrium point, and you can tell that because the partial pressures become constant. So that is where I will just formally mention the definition. So part B is over here. And the qualities of equilibrium are, 1, the partial pressures or concentrations of the reactants and products cease to change. Now, this is after infinite time and at a given temperature. Now it turns out you can also, and we will, define equilibrium in terms of kinetics and rates. But for now, we're just defining it in terms of the partial pressures and concentrations ceasing to change. Now, another important point about equilibrium and its definition is that there's still reaction going on. So the forward and reverse reactions are still happening. So even though the partial pressures in this case are not changing, we still have, at equilibrium, some hydrogen and nitrogen colliding to form ammonia, and some ammonia breaking down to form hydrogen and nitrogen. Now, mathematically, it turns out that when these partial pressures, or concentrations, as the case may be, are unchanged, mathematically, this is represented by this definition here, where we put the partial pressures of the products on the numerator and raise it to, in this case, the power of 2, because that's the coefficient in the balanced equation. And then for hydrogen, we raise it to the third power, and nitrogen, we don't raise it to any power. This ratio of products to reactants raised to the powers from the balanced equation, this is constant at equilibrium. And we represent this with the letter K. And in this case, because we're dealing with partial pressures, we call it K sub P. If we were dealing with concentrations, then this would be K sub C. We'd have concentration terms in this ratio. So what does this mean? What's the utility of this? Well, it turns out if someone gives you an equation, a reaction, and they give you the equilibrium constant, there are only 3 cases. So this is part C now. Excuse me, part C, in which if someone gives you this reaction and then gives you K, you can determine the dominant species in the reaction vessel or flask. So if you look at this ratio here, if the p-value if the numerator is large because the partial pressure of the product is large, you have a lot of product around, inherently the denominator will be small and your K will be large. So this is a case where we'll say if K is much greater than 1, the dominant species will be products. And between chemists we would say, well, that reaction goes to completion. There'll still be some reactants in there, but it will largely be products. Now if we look at the inverse of that situation, where we now have large partial pressures of hydrogen and nitrogen, inherently we won't have as much ammonia, the reaction will have not proceeded. This ratio will thus become much smaller than 1, the denominator is large, so now we say the vessel has largely reactants in it. And then of course the last circumstance is if the magnitude of the numerator and denominator are comparable, and I like to say somewhere between 10 and 0.1, then you definitively have a mixture of reactants and products. So next time I'll talk about situations where if given initial values of partial pressures for hydrogen, nitrogen, and ammonia, you can tell whether the system is at equilibrium, and if it's not, how the partial pressures will change in order for that system to get to equilibrium. Thank you very much.